Good afternoon and welcome to today's webinar, Household Carbon Reduction Part 2, Building Sciences Connection. I'm Matt Reese, GreenGov Council Deputy Director. Today's webinar is co-hosted and supported through our partnership with Penn State Sustainability Institute. The GreenGov Council was established by Governor's Executive Order 2019-01, which requires Commonwealth agencies to lead by example, promoting energy conservation and sustainable governance. The executive order sets goals for the Commonwealth, including the goal of achieving a 26% reduction of greenhouse gas emissions by 2025 and an overall 80% reduction by 2050. The executive order created specific goals for agencies on fleet electrification, high performance buildings, annual energy reductions, and use of renewable electricity. Visit our website at dgs.pa.gov/greengov to see how agencies are meeting these goals. You'll find a host of information on the website, including past completed agency certification checklists, past annual reports, and GreenGov news and opportunities to sign up for the GreenGov newsletter and other future webinar series. Now I'd like to introduce our friend, colleague, and partner at Penn State Sustainability Institute, Dr. Peter Boger, PhD. Peter is the Assistant Director for Community Engagement at Penn State University's Sustainability Institute and is responsible for developing strategic programming and partnerships such as this one with the GreenGov Council that help Penn State leverage its resources to promote sustainability throughout the Commonwealth of Pennsylvania.
Thank you so much, Matt, and thank you everybody for joining us today. As we've mentioned before, we are excited to be in this partnership with the GreenGov Council because we both are on the same mission. We are both small, nimble teams trying to help much bigger institutions with their goals. And since Matt and Mark by themselves can't change state government, and neither can the 9 of us in the Sustainability Institute change all 24 campuses in the Penn State system, we both see ourselves as conveners and catalysts to change. And it's events like this where we can bring people together and hopefully catalyze new collaborations, new ideas, and help you become the change makers in your organizations. And so we are delighted to see this series continue for its 4th session and look forward to many more this year.
Well, thanks, Peter, and we certainly appreciate this partnership, and it's certainly been a fantastic resource for us as we go forward, and for that we are greatly appreciated. Next, I'd like to introduce. Sorry. Next, I'd like to introduce our guest speaker for this afternoon, Jon Kautz. Jon is a member of the PA Housing Industry Advisory Council and founder of the Energy Smart Home Improvement. Jon opened Energy Smart in 2007 and has been committed to improving the performance of the built environment through the application of strict industry guidelines ever since. Jon's background is exclusively in building sciences, including 9 years working in research and development for a Fortune 500 building manufacturer, several positions for national performance building product manufacturers, and extensive field experience in the local building industry. Jon and his team maintain a variety of certifications through industry-leading entities such as Pennsylvania Housing Research Council, Building Performance Institute, Northeast Home Energy Rating Systems, the National Association of Home Builders, and the Harrisburg Builders Association, among others. Jon's team are also approved contractors with Keystone Help, First Energy Whole House Program, and PPL Electric Utilities Home Comfort Program. Jon is a former sprint car racer and still enjoys races whenever he can. Other times he is found with his sons visiting Go-Kart tracks or as a spectator at one sporting event or another. While home, Jon can be found enjoying time with family as much as possible and sneaking in a round of golf as weather permits. And take it away, Jon.
Well, thank you very much, Matt. It is great to be here today, and I want to thank the PA GreenGov Council. And today we're going to do a painful topic, the building science connection, and how it relates to carbon reduction. So let's get in and dig right into this. My company is called Energy Smart. We're a home performance company, which means we understand the science behind houses, and we apply that in providing solutions to problems in homes, problems such as comfort issues, high energy use, those sorts of things. I am a BPI building analyst. which means I understand the science behind residential construction. And then also I serve on something called the Industry Advisory Council, which is a portion of the PA Housing Research Council. And basically what I do is I'm a liaison between the real world. In other words, I see hundreds of houses every year. I bring what I see in the field back to the research environment, and we pick research projects that they perform at Penn State University, and then we present papers and do a lot of ongoing education for builders and codes officials. Let's get into it. Our purpose today is to shed some light on our investigation into a very serious crime and how we brought the culprits to justice. Thanks for joining us. First, we have the accused, and we're looking at the accused, this residential home that's actually located down in Chambersburg. This building is accused of excessive energy consumption and poor indoor comfort. So let's begin the investigation. Reducing our carbon footprint begins with an energy assessment of some sort or an energy audit. An energy assessment allows us to investigate the causes of home inefficiencies and offer cost-effective solutions. So the key here is that we're going to try to use a scientific approach and find the most cost-effective ways to make houses work better. And this is going to reduce our carbon footprint, reduce our energy bills, increase home comfort, and reduce our impact on the environment. Science. We need a basic understanding of building science if we're going to make informed decisions about our homes. First of all, there are three methods of heat flow: induction, convection, and radiation. Let's talk about each of these individually very briefly so we can get a feel for what we're really looking at when we want to look at a home and decide what we can do to make it function better. First of all,
13 states that have persistently high rates of cigarette smoking.
First topic is conduction. That's something that most people are familiar with respect to energy use. It's familiar, it's predictable. This is heat conducting through solid objects. When we touch a hot frying pan, that is conduction. Mostly we think about insulation when we think about addressing the issue of conduction of heat. So insulation is going to slow down the conduction of heat. Just a couple examples of attic insulation and wall insulation. A less understood method of heat transfer is something we call convection. Convection is heat transfer by moving fluids like air and water. As a practical matter, we mostly talk about air as being the medium when we're talking about convection in homes. When we blow on a cup of coffee to cool it, that's an example of convection. When we talk about convection in the home, we're typically representing it as what we call air infiltration. That's usually the term that we're going to use. And an important concept to remember is that insulation, in most cases, does not stop air infiltration. So when we think about insulating an attic, in most cases, that is not going to address the air infiltration in an attic or other places. So we really have two different things that we're looking at. When we think about air infiltration in a home, you know, it's just natural to say, oh, it's my windows, my doors. I mean, that's where all the air is leaking in and out. And nothing could be farther from the truth. So what we're looking at as energy professionals is a phenomena called stack effect air infiltration. This is the dominant way that air moves in and out of your house. This is the thing that we want to really concentrate on controlling today. So looking at the diagram that we have here, when we go down low in a house, into a basement of a house on a very cold day, the air pressure in the basement is lower than the air pressure is outside. Consequently, we get cold air coming in low in a house. Typically, the most common place that this air comes in is where the wood framing sits on top of the foundation. We call this a rim and band detail. Once this unconditioned air enters the home and the building envelope, it heats up and rises. When we get to the top of the house, now our air pressure is higher inside than it is outside, and the air is trying to exfiltrate high. Typically, those exfiltration points are going to be interior and exterior walls, wire penetrations, plumbing penetrations, recessed lights, all those sort of things. So we really want to concentrate on the bottom and the top of the house when we want to address air infiltration in a home. I like to call it the hat and the socks. That's really what we want to address. This is an image of the socks, if you will. This is where the wood framing sits on top of the foundation in a basement. And you can see from the infrared image here that we are allowing a lot of cold air to enter the building envelope right here. And that's something that we really want to correct. On the opposite end, here is an example of an infrared image of a wall at the top of a house. And here we can see the cold air exchanging from the attic into the wall cavities. Here's a little bit wider shot of the same thing. So once again, a lot of air movement between the upper floor of a house and the unconditioned attic above. Same thing's true for penetrations. You know, if we have a recessed light penetration, we're going to typically see that air exchange between the attic and the house as well. Moving back lower in the home, if we look at the baseboard detail, which is directly above what we call the rim and band, or where the framing sits on top of the foundation, we can see that that's an area of a lot of significant air infiltration and some of the draftiness that makes you uncomfortable in a home. And ditto for a wall. So we've talked about conduction, we've talked about convection, and last is radiation. Radiation is heat flying through space from one object to another. It's a direct line of sight, so a straight line shot. The analogy that is probably is easiest for me to understand, at least, is I remember as a young lad, I was a lad, and we would sit by the campfire. And as long as you had a direct line of sight from your body to that campfire, you would feel very, very warm. All it would take is someone to stand between you and the fire, and almost immediately you would realize that you're getting cold very quickly. So that is an example of radiation and how that works. The opposite example of radiation occurs in a house. And I think this is an important concept to think about. So we have a nice warm body, and if we have cold surfaces in the house, so if we have uninsulated walls, if we have an uninsulated ceiling, that heat from our body is radiating off onto those cold surfaces. So we could have actually two different rooms in a house that are both the 70-degree temperature inside them. One, you could have a much greater perception of cold than the other, based on the radiation and the heat radiating from your body. And there's my campfire right there. So that is the basics where we get started, the basic building blocks: conduction, convection, and radiation. So how do we determine the scope of work when we're trying to decide what to do on a home performance contract or project? Scope of work is determined by the specific needs of a client. Many of our clients come to us because they have long-term environmental concerns, and we typically address these concerns by creating a descending order list of problems in a residence, and this list is based on the effectiveness, oftentimes the cost effectiveness. Comfort issues is a reason that we get called into homes very, very frequently. The beauty is when we're fixing a comfort issue in a home, we are at the same time addressing the carbon reduction and energy use. And some of our clients are just really concerned about return on investment and have less of an inclination to be concerned about other things. So people improve their homes for a number of different reasons. When we want to address energy in a home, we have a very specific order that we want to use, and it's based on typically on cost effectiveness again. So energy conservation is something that's very, very cost effective, costs almost nothing to make sure that you turn lights out, that you use as little hot water as you can, or keep your hot water heater at 120 degrees. So all of this is free stuff. Sadly, if you have any teenagers in your home, good luck on that one. Then next on the pyramid is energy efficiency. So that can include adding insulation, sealing air leaks in your house, using Energy Star appliances. So that's the next level of cost effectiveness. And then lastly, we get to the renewables. And renewables, an important concept really to think about here is we want to make our homes energy efficient before we add renewables typically, because renewables are more expensive than the energy efficiency portion. And most of the time, if not all of the time, when we make our homes more energy efficient, we don't need as many renewables to supply our needs. So when we're prioritization of reducing home energy consumption, we want to do this in a specific order as well. The first thing we want to address when we're trying to make a house more efficient and reduce our carbon footprint is building shell issues. So in other words, how are we going to try to keep the heat that we produce in the wintertime inside the house instead of outside the house? And of course, we do that through the different means of heat transfer: conduction, convection, and radiation. So we want to make our building shell work well before we do anything else in our home. The next step then is mechanical equipment, upgrading our mechanical equipment to have more efficient use of the energy that's there. Now, the reason that a building shell should be addressed before the mechanical equipment is because oftentimes when we address a building shell and make it more energy efficient, we can downsize the mechanical equipment that we use. And so that's really an important thing to consider. And lastly, we want to address our base loads in a home. So base loads are lights, appliances, and hot water. Typically, there's not as big a pool of opportunity in those areas without changing pretty significant things to our lifestyle. And lastly, our prioritization after we've done all of the things to reduce our loads in the house is to add the renewable portion. So the building shell issues, once again, conduction, convection, and radiation. And those are the different things we're looking at when we're trying to make improvements to a building shell. Mechanical equipment, we're primarily talking about heating and air conditioning equipment and water heating. Base loads, once again, are our appliances, our lighting, and electronics in the home.
One example state, we're going to look at Tennessee. That's because Tennessee has one of the.
There we go. I think we're back. Then lastly, we talk about the renewables. And of course, we're looking at most commonly solar PV, solar hot water, and wind. So the usual suspects, who are we after when we typically go into a home? And these are some scary looking dudes here. Basement, attic,
So this graph
crawl
shows
spaces,
over time compared to a scenario where
pod details, and bonus rooms. These are the 5 different areas in homes that we typically are going to address in more homes than most other details that you might get involved in. Our top 5 remediation projects in homes: addressing the air leaks at the basement, rim, and band detail is probably the most common one that we do. Attic remediation, which is going to involve sealing air leaks and insulating attics properly. This area is a very common area for a lot of crawl spaces. I think a lot of that is because of the limestone foundations or the limestone that we have in the ground here that oftentimes makes excavating difficult and expensive. So we have a lot of crawl spaces. Most of them don't work very well. And then Cape Cod details. We have a lot of Cape Cods that were built in the 40s and the 50s in the central PA area. These typically have very, very high air infiltration rates. And the last of our usual suspects is bonus rooms or rooms built above garages. And these typically are very uncomfortable rooms, primarily because they have more of the sides of the room that are exposed to unconditioned areas. So basement rim and band detail. This is air sealing where the foundation meets the wood framing. Due to stack effect air movement, this typically reduces overall air infiltration by about 10 to 20% in a typical home. So it's a big, big area, an area where we're going to get a good return on investment. We're typically going to use 1 or 2 part spray foams is the most common way that we're going to address the air leaks and the conduction issues in these areas. The detail that we're looking at, this is a shop drawing, if you will, of the rim and band detail. So we have a sill plate, a piece of wood that sits on top of the foundation. We have a band board, and then we have the subfloor where your feet are in the living space above it. The gaps in between each of those areas is where the cold air comes into our house, and also that's where the bugs come into the house. So it's kind of just a side benefit when we air seal these areas. Typically, we're going to take that area and we're going to use spray foam. In this case, we're using about a 2-inch application of spray foam. Now we've sealed all the air leaks, and we've also provided a significant amount of thermal protection through the R value of the spray foam. So that's probably the most common thing we do in most houses, is stop where the cold air comes in low. Next most common is going to be addressing attics in a home. We're going to insulate and air seal, and that's very, very important that we do both of those. We air seal all the top plates of the walls, pipe penetrations, wire penetrations, chimneys, and recessed lights. Today we insulate to a minimum of an R49. So our codes require an R49 in our area of the country. But for Energy Star's recommendations, we're going to have a minimum of an R49 and an optimum of an R60. This is an image of someone spray foaming in an attic. The area where his spray foam gun is right now is the top of a wall. At the top of a wall is a 2x4, and on each side of that 2x4 is drywall, and there's gaps between the drywall and the top plate. That's what he is sealing right there. So what we do when we air seal an attic is we're going to move the existing insulation in a retrofit application and address those as they're going along the top plates. They're going to find wires, they're going to find pipes, they're going to find receptacle boxes. We want to spray foam all of these areas if we want to have a really effective building shell. In new construction today, with the current codes, now we do have to air seal every attic, and we've had that as a requirement for some period of time. In the 2018 building codes in Pennsylvania, where we're at right now, we do have fairly strict requirements in terms of air infiltration rates. We are only allowed to have 3 air changes per hour at a 50 Pascal difference in air pressure with any new builds that are under the 2018 codes today. So we really have to tighten up the building envelope pretty effectively. Next, we're going to add insulation. Typically, we can use a fiberglass or a cellulose insulation. Us energy guys like the cellulose insulation a lot more than the fiberglass because we are going to get a lot better wintertime performance because it's a much more dense product. With fiberglass, we get what are called convection loops in an attic, and that's where the embodied air in the fiberglass that's sitting next to your ceiling, it's nice and warm embodied air. As the air in the attic above it gets colder and colder, it gets heavier and heavier and denser until eventually it displaces the embodied air and reduces the effective R value. So we're typically going to use something that performs a little better than that. Crawl spaces. Crawl spaces are one of the least understood areas of a home. Typically, the way we've addressed crawl spaces is we put all these vents in the side of your house, and supposedly that's supposed to get all the moisture out of there. Highly, highly ineffective. The way we've done crawl spaces forever has never worked. What we typically see in crawl spaces in central Pennsylvania is we see a dirt floor. Usually the moisture level in that dirt floor is usually 80% or more. So we're just putting tons of moisture into the house. We remember this stack effect air infiltration. Everything's rising in the house. So what is going on in that crawl space is what you're breathing in your house. So it's really important, not just for reducing your carbon footprint, but also for your health and safety as well. We have to have effectively defined pressure and thermal boundaries in a crawl space for it to work well. So the first thing we have to do is get rid of the moisture. So what we typically will do is install a liner on the dirt floors, and that's going to provide our pressure boundary down on the very bottom of the crawl space. A lot of people use a polyethylene, not very effective. It doesn't air seal very well, and it's not very durable. We typically will use a roofing membrane, something called thermoplastic polyolefin. It's actually, if you ever looked at the roof of a Walmart, which I don't know. I mean, if any of you have looked at the roof of a Walmart, you need to reevaluate your life, I think. But that being said, that's the membrane we typically like to use on the floor of a crawl space. We also, once again, just like a basement, we have to air seal the rim and band. Once those things are done, we can then close the foundation vents because they don't serve a purpose anymore. And we're typically going to insulate the side walls or foundation walls. So this is what an application like that, what that might look like. Not necessarily particularly pretty, but highly effective. Next, we jump on to Cape Cods. So the problem with Cape Cod details in homes is there are no effective or aligned thermal and pressure boundaries. So we tend to have super, super high air infiltration rates. And almost always when we have a Cape Cod detail that's not done correctly, we're going to find big differences in temperature between the first floor and the second floor. We are going to establish the pressure and thermal boundaries either at the knee walls or we can do it at the roof joists. And that really is dependent upon the specific details that we see at any given house. This is one of the most misunderstood energy details that we have to deal with. This is what they look like. Once again, we need our pressure boundary and our thermal boundary at the same place. So on the left side, what we see is we've put our insulation in the roof joists and we've provided an air barrier on the underside of the roof joists. So we need our air barrier and our insulation aligned in the same place if we want it to be effective. When we do that, we've created a conditioned space in the knee wall crawl space. Alternatively, oftentimes we will choose to create the pressure and thermal boundary at the sloped ceilings, the knee walls, and the knee wall crawl space floor, as we see in the right example. In that case, the knee wall crawl space is unconditioned space. Once again, it's a matter of establishing a pressure and thermal boundary that are aligned if we want this to be effective. And last of our top 5 usual suspects is bonus rooms. Garages are generally poorly isolated from living space above, and this is really important on a number of different levels. The first and most important level that's important is we have to realize that in most cases, what is going on in your garage is what you're breathing in your bonus room. So we want to be very, very sensitive about running cars in garages, sensitive about the chemicals that we have in garages. That's something when we do remediation there, we're going to really improve that a good bit. Typically what we find is misaligned pressure and thermal boundaries at the attic ceiling. So what happens is typically in modern construction today, we're going to put typically R30 fiberglass bats in that space between the garage ceiling and the floor of the bonus room above. What almost always and invariably happens is that that fiberglass settles and creates an airspace in there that allows unconditioned air to render that insulation very, very ineffective. The remedy that we typically do today is we want to eliminate any unconditioned air from that space between the garage ceiling and the floor of the bonus room above. We typically use a technique called dense packing of cellulose. So we put little holes in the floor, or I'm sorry, little holes in the ceiling of the garage, insert fill tubes, and we pack that very, very tightly with cellulose insulation. When we can achieve a density a little bit over 3 pounds per cubic foot, we eliminate any air movement in those spaces. So it's a very, very effective way of it not only is reducing your carbon footprint, but it's also increasing comfort significantly in the bonus room itself. So we need to arrest the culprits, in other words, resolve the problems. And if we do the things that we talked about in our top 5, we got them. And that is it. I want to thank you. This is one of my crews at Energy Smart right here, and they will provide entertainment value as well as effective methods of reducing our carbon footprint. Thank you very much. I appreciate it.
Well, thanks, John, so much for this fantastic presentation, and we will now stop the recording.